Hi, my name is Anjana Murali and I'm a junior.
I'm Anya Murali and I'm a freshman.
And we are both students at Shorewood High School in Shorewood, Wisconsin, and we did our project on thermoelectric energy. Essentially, we were investigating an alternative energy source in these thermoelectric crystals. And right now, we are in ISWEEEP in Houston, Texas, presenting our project at the international competition.
And the crystals that we used for this experiment are called pnictogen chalcogenides, and they are found in groups 5 and 6 on the periodic table. What's special about pnictogen chalcogenide crystals is that they have a special property called a thermoelectric property, which gives an easier way to generate energy, because all you need is a thermoelectric material and a temperature difference. For our experiment, we used a hot plate as a hot junction and a continuous supply of running tap water as our cold junction.
And the essential basis of this phenomenon is actually very simple. As you know, the electron is the only mobile charged carrier in an atom. So when placed in a temperature gradient such as ours, the electron moves to the cold junction, leaving behind its oppositely charged nucleus at the hot junction. This then gives rise to an electric potential that we took advantage of and harnessed voltage from to hopefully generate energy.
And we had 3 main questions we wanted to address through this experiment. The first question was, are we actually able to generate energy from these crystals? And the second question was, how the effect of adding impurities would affect the voltage in these crystals from a pure sample to a sample with added impurities. And we used 3 main impurities in this experiment. We used 3 transition metals: copper, manganese, and zinc. Our third question was, how does oxidation play an effect in the generating voltage?
As you can see, these are the results from our experiment. The first graph shows that yes, in fact, we are able to generate voltage from these crystals. And this is actually a very big deal because as far as we know, we've done research on various researchers on their experimentations with thermoelectric crystals. We are the first ones to actually conduct an experiment such as this one in room temperature. There are very few papers on this topic to start off with, but the researchers who have done experiments with thermoelectric crystals have used liquid nitrogen as their cold junction. So obviously they're getting huge temperature differences since liquid nitrogen is such a cold substance, and they're consequently getting huge voltages. We, knowing that one day hopefully our experiment will be used to create an application that we can use in real life, thought that it's not that feasible to generate a substance like this that will, use liquid nitrogen, because you can't just freely hand out liquid nitrogen to the public. That's why we wanted to set up our experiment at room temperature, so that if it worked, we can actually apply it to real life and use an application of this setup to generate energy in our real world today. So from this graph, you can see that we did in fact get voltage from these crystals, and we transferred this voltage into the Seebeck coefficient as a way to compare all of our results. And so in room temperature, with these crystals, you get about 0.04 worth of a Seebeck coefficient, which is awesome. Our second question was answering the question of whether impurities in these samples will hinder or help us in our quest for generating energy. And as you can see, with intercalation, intercalation is a fancy word for introducing impurities into the crystals, the Seebeck coefficient produced is less. So when generating these crystals, it's best to avoid introducing impurities, because you will lower the amount of voltage that you get.
And this project is actually a 2-year project, and it's a continuation from the project we did last year. And as you can see from this setup, we use the same general idea, using the hot plate as a hot junction, but we used air room temperature as our cold junction. And that's what these two graphs are from, our experiment last year. And we saw that, yes, we were actually able to generate energy, but we saw that over time, the copper plate that the sample was on was starting to turn blue and purple, which are signs of oxidation. So this year we did our experiment to see what the effect of oxidation was, and if we could generate higher voltages by using an inert atmosphere.
So we attached an argon tank to the apparatus that we designed to eliminate any effects of oxidation, and the results are clear. These three graphs are from this year's experimentation in an inert atmosphere, and as you can see, without oxidation, so in the inner atmosphere, you produce much higher Seebeck coefficients, which means that we're producing much more voltage. So in the argon systems, we saw that we were getting Seebeck coefficients of around 0.3 compared to the ones done in regular room temperature, which produce about 0.04 worth of a Seebeck coefficient, which is a huge difference. As Anya mentioned before, we investigated 3 main systems, and we wanted to see which system would be best for producing a thermoelectric sample.
So from what Anjana said, our second question was the effect of impurities. And as you saw in the normal room temperature examples, you can see that adding the impurities drastically lowered the Seebeck coefficient. And the same goes for in the inert atmosphere. So here is our pure sample, which generated about 0.25 as a Seebeck coefficient, whereas the samples with the impurities generated almost nothing. And we saw the same trend in all 3 graphs, but we saw that in bismuth selenide and bismuth telluride, the graphs actually they either leveled off or they even decreased, giving it a negative slope as the temperature difference increased. But in the antimony telluride system, we actually saw a slightly different trend where the graph actually increased as the temperature difference increased.
And this is a simple but very important observation, because one thing that we, thought of as we were doing our experiment is that it's not possible to generate a perfectly pure crystal in our world. I mean, in an ideal world, sure, that could be a possibility, but impurities are everywhere and they can easily get into the synthesis process of these crystals. So this trend that we saw in the antimony telluride system gave us hope, because it showed us that even with the introduction of impurities, a simple increase in the temperature difference should be able to override the effect of impurities and therefore generate just as much voltage as a pure sample would. So we would recommend using the antimony telluride system as an application in our real world. To say the application of these crystals is one of the most remarkable things you can get from our experiment, because there are so many natural occurring temperature differences in our world. Take your car, for example. If we place one of these crystals on the hood of your car and have the generator below create excess heat, then as you drive, the cool air rushing above the crystal would act as the cool junction, with the generator below acting as the hot junction, giving rise to a perfect temperature difference that we can take use of and maybe even power the GPS in your car or charge the iPhone in your car and help you save money in that way. So the application of these thermoelectric crystals are far and wide, and we hope to someday commercialize our project and use it to make a safer, greener world.